So I'm really delighted to have you here, Michael. First of all, welcome to this Skirball series, Paradigm Shifters.
Thanks.
So Michael Strevens, you are professor of philosophy at NYU. You're the author of several books. You're a philosopher of science. The book that I knew before The Knowledge Machine was Depth, an account of scientific explanation. And you also have a book called Thinking Off Your Feet. And what I'd love for you to tell us today is you're interested in how science became as powerful and persuasive and having this kind of force for the good in the world. And The Knowledge Machine is really an account of how modern science came to be. And then there's two specific interests, as you know, I have, and why we're so excited to have you on the series. Your two sparring partners or intellectual protagonists are called Popper and Thomas Kuhn. And I would love to have you sort of walk me through how they conceived of science and what you add, which is that you are making this argument that there's a very deeply irrational part to how science actually operates.
The really interesting thing about Popper versus Kuhn is that they have such completely opposed ideas about why science is so powerful. On the one hand, Popper has the idea of the scientist as the ultimate critical, rational machine, someone who never takes anything for granted, who's always looking for the flaws in ideas, who's always trying to uncover the ways in which they're going wrong. And for Popper, this critical attitude is absolutely at the heart of science and its ability to discover things about the world that we philosophers for thousands of years, for all the good we did, never came close to managing. Kuhn, on the other hand, has the idea that scientists are effective precisely because they lack a critical attitude. Now that seems a little peculiar. And there's a sense in which Kuhn thinks that, agrees with Popper, that science is so effective because it's able to find very small discrepancies between what a theory says and what's actually seen in the world, discrepancies which lead to a complete overthrow of prevailing ideas and the kinds of new ideas, the idea that it's the sun that's at the center of the solar system and the earth is going around the sun, not vice versa. Or Einstein's theory of relativity, quantum mechanics, Darwin's theory of natural selection. These huge new ideas come along because things are just not quite right with the prevailing ideas. So these little facts are the keys here. Kuhn agrees with Popper. Popper has his scientists ferreting out those facts because they're overflowing with eagerness to prove the current theories wrong. But Kuhn's idea is that the scientists have no expectation that the theories will be wrong. In fact, they're convinced that they're right. And what they want to do is use those theories to flesh out our ideas about the way the world works. So Kuhn calls these theories and all of the presuppositions and priorities that come with them paradigms. That's his famous work for these things. And the scientists are absolutely gripped by the paradigm. They want to use it to complete our human picture of the way the world works. But charging in with the theory and forcing it to do everything, they inadvertently, accidentally, if you like, turn up the little discrepancies that, as with Popper, end up refuting the prevailing ideas, and the new ideas come marching along.
And in the Kuhnian description, scientists find these things which don't quite fit in. And I want you to say a little bit more, because your book has these amazing examples of people finding something that doesn't quite mesh with the theory. And in Kuhn, initially they dismiss them, or if they're small enough, you say that's just a blip, or that's just another finding, let's redo the whatever experiment or whatever we do, or let's observe more, and it will ultimately fit into how we think. And this paradigm is kind of a habit or collection of ideas and procedures also. So scientists need to be in it because you can't do science without sort of accepting some procedures will be done. You have to have clean equipment, etc. And in Popper, well, how you describe these scientists, they're these kind of destructive, sort of eager, like trying to find fault with something. They want to falsify. They're just looking for the thing that doesn't make sense in the theory. And that's right. Both will encounter these things, right? Both scientists will come across stuff that doesn't fit into their theory. And then Popper goes in a different direction, and he says the strength of science is there's no theory that can be proven, if that's right. It can only be falsified, right?
That's right. Yes, so with, as you say, with Kuhn scientists are so convinced the paradigm is correct that when things go wrong, they think, well, I must have done the experiment wrong. Now, this is a very, I think this is a very apt observation of Kuhn's. So things go wrong in science all the time. It's usually the case, in fact, that when you get some odd experimental result, there's something wrong with your equipment. Some small animal escaped, chewed through the wiring, a cable was loose. Mm-hmm. So these scientists who think, well, it was the equipment, not the ideas, are not really engaging, at least at first, in any kind of absurd special pleading. Usually what you need to do is check everything, and then things come out much more nicely the second time around, or the third, or sometimes the 10th. But in Kuhn's telling of the story, they'll just continue to ignore these problems even as they mount up. And they'll become more and more frustrated, more and more disappointed, more and more disheartened, but they still won't consider themselves to have actually refuted the theory. Whereas Popper's scientists are looking for refutations as soon as they see a mismatch between theory and observation, they jump on it. So with Kuhn, for a long time, you get the excuses build up. And there is the morale sinks. Everyone gets confused and disillusioned, but they are still not contemplating the idea that the theory might be wrong.
And in Popper, it's not, we can't really, and these words are really specific, and I'm really interested, I'll ask you at the end of this conversation, why the word paradigm becomes its own paradigm. Actually, it's used everywhere. I use it in a totally different way. But when the scientists in Popper, they're not constantly looking out to overthrow a paradigm. Kuhn says it's a practice, it's habits, it's things, assumptions. You go to the lab, this is how you work, or whatever you do, or you observe things in an observatory or in nature. And what happens when a scientist in Popper discovers something that falsifies the theory, he keeps on doing it and says the theory doesn't explain this thing. That is not where Kuhn wants to go. Then there's what he called originally, I think, the revolution, which we now call a shift. So what happens in the theory when the Popper scientist figures out something isn't working here?
Are you asking me according what Popper thinks happens, or what?
Yeah, and then you can tell me what you actually think happens, right?
Yeah. So, yes, I guess there are three distinct stories here. The characteristic Popper story, the characteristic Kuhn story, which I just told, and my own story, which I think is more accurate, and which is, I think, many sociologists, historians, and philosophers of science would go along with. So in Popper's story, we discover a problem, and we say, well, there's something wrong with that theory, obviously. I mean, Popper did, of course, realize too that sometimes the equipment is dirty, and so we can't just throw out a theory because we have one peculiar observation. We have to go back and make sure we get the same mismatch over and over again, the same missed prediction over and over again. But once that happens, we do what we can to change the theory to make it better. So we might at first make a relatively small alteration in the theory so that it's now compatible with what we observed. And then another, and then another. We'll always be trying to test those extra assumptions we're making, because for Popper, the heart of science is this critical attitude to every assumption you make. Right. Whenever you make an assumption, the first thing you do is try to prove it false. But eventually, if the smaller changes don't work out, then we may need to completely replace the theory. And for Popper, this is a completely rational process and a completely clear-sighted process. So the scientists always know that they have a problem. They're always considering the possibility the theory as a whole may be completely mistaken, and they're always on the lookout for something new and better. Whereas with Kuhn, they can't conceive that there's a problem. They feel bad, but they see no alternative. Kuhn calls this a crisis in science, and it's a kind of a moral crisis as much as it's even perhaps more than it's an intellectual crisis. Eventually, the whole system, the whole paradigm becomes unsustainable. Somebody comes along with a new idea, and then we have what Kuhn calls a scientific revolution, a paradigm shift, and the new idea somehow takes hold, but Kuhn famously says it's not an entirely rational process. It's more like a religious conversion experience.
And what you're saying for Popper, you revise a theory, maybe you have to adjust much of it, but ultimately you end up with another theory. For Kuhn, however, once a generation of people steps out of a paradigm, they're totally incommensurate. And there's this famous anecdote that he has when he was in Harvard Yard looking out the window and Aristotelian physics made no sense. And then he said, but it made sense to Aristotle and that worldview, and it's entirely coherent within that. For us, it is inconceivable that this would explain the world. So he actually says what he calls paradigms. They're incommensurate. You cannot inhabit both of them. You can either think the sun is the center of our solar system or the earth is the center, but you cannot sort of say, well, sometimes I like to believe this and sometimes I like to believe that. Right? So he gives you these incredibly exciting examples of these huge shifts.
So because the paradigm is like a worldview, it's like one way it's like a religion. You can't really have subscribe to two religions at the same time. That's just not the way the whole religious mindset works. And likewise, Kuhn says with the scientific mindset, it's not just a belief about certain aspects of the structure of the universe. The earth is at the center, the sun is at the center. It's a whole way of looking at the world. It's a whole way of explaining what goes on in the world. It's a whole set of values, a whole set of procedures that is a way of living your life as a scientist. So it's not easy to give up. And when it does happen, it happens in this desperate, chaotic, almost crazed way, and yet ultimately for the good.
Right. I'll ask you a question about this a bit later, about whether Kuhn believes there's ultimately progress in these kind of successive paradigms. But to go to your book, The Knowledge Machine, so you looked at these two models, which are very powerful explanatory model for how science actually works. And you're more interested not just how it works and creates results, but what are the assumptions or the premises why science of all things became so incredibly successful. And I always like when you write, and your book is just beautifully written and it's very entertaining and it illustrates all these complex examples. And you say, well, I'm a philosopher. I wish philosophy was that successful, but philosophy never attains this level of importance in the world. What happens in science, and what is this idea that you have that there's something irrational that makes it so powerful for us?
Well, I think that Popper and especially Kuhn are right that these little facts, these little mismatches are really the clues that will change our worldview for the better. And if we go back to the way that people inquired into the structure of nature before modern science came along, so we look at, say, the way Aristotle did his kind of Greek science, what we see is much less of a concern with these small mismatches. The aim is to get the story qualitatively right, to explain the kinds of things that are seen, the kinds of patterns of motion of the planets across the sky, or the patterns of falling objects, or the patterns in the behavior of living things. But not to concoct a theory that tries to predict the trajectory, say, of a falling object to a very precise degree. Now, for all anyone knew in those days, these minute observations would be completely worthless. Every time things happen, they happen a little differently. So all you're doing is making a big long list of the little differences, and that is of no interest whatsoever. that belief turned out to be completely wrong. It turned out that these little differences are actually very consistent, and somewhere in there is the information that will tell you that it's the Earth going around the sun, that it's gravity pulling things to the Earth, or even more precisely, that it's not gravity, it's the curvature of space-time, as Einstein said. So what was necessary in order for modern science to come along and give us this amazing power to really learn the secrets of nature? It's hard to talk about this stuff without something like Carl Sagan. Maybe that's a good thing.
But that's your interest. Ultimately, you're thinking it has this kind of far-reaching consequence. It is to unlock the secrets of nature, right?
That's right. That's why I've always been fascinated by science. I'm not a scientist, but I'm a philosopher of science. So science is, in a certain sense, my life too. But it's these little facts, and people had to, the thinkers had to first of all realize that it was worth paying this kind of attention to the little facts, and then create a kind of system. And this is where Kuhn's ideas are especially interesting, I think. A kind of system for motivating people to devote all of their time to making these minute observations, or describing very intricate structures. So I think that's where Kuhn's paradigms are his explanation of why scientists are so motivated to pay attention to what would have looked to Aristotle like minuscule, uninteresting ephemera, these little differences. Right. And the idea is not that scientists see that the differences are really important, but that they're so taken with the poetry of the paradigm, if you like, that they just want to make sense of everything. They want to fit everything into the paradigm. So they have this drive to even fit the small differences in. Once they've made sense of the big differences, they turn to the small differences and they say, yes, we're gonna even this will fit the paradigm. Right. And that's where things start to go wrong in a most fruitful way.
And fruitful in what sense? What do you mean? Like, why?
In the sense that scientists discover, first of all, that the small differences are consistent. It's not just a big noisy mess. If you do the experiments carefully enough, time and time again, you get slight deviations from what your theory was telling you. And then the other thing is the paradigm tells you that this really matters. So it's really essential to the paradigm that it get everything right. It's not enough that it be roughly true. It has to be true in a completely total and exceptionless way. Again, like a religion, it's not enough that the doctrines of religion be more or less on the right track. If you're a believer, you believe that that is the truth. So this is what creates the dissatisfaction ultimately with the paradigm as it exists, and prepares scientists to make the jump to the new religion, or rather the new paradigm, the new theory.
And can you talk about this example you give in your book, which becomes very important in your argument, where we have a shift from Newtonian to Einsteinian physics? It's when they go and try to observe a solar eclipse. I think they go to the southern hemisphere to travel to look at it. And I remember hearing this anecdote actually in Owen Gingrich's History of Science class. And there was a very funny anecdote about Einstein's response to the findings of this expedition. But can you say something, what happens there? What are they looking for? And then how you explain what they did actually?
Yes, I'll talk a little bit about that, and that will show the ways in which it seems like Kuhn's own picture doesn't quite get the details right. Yeah, right. So we need a paradigm shift from paradigms. So Eddington proposed this expedition that took place right after the First World War. The idea that Einstein's theory had only really just been proposed in 1915, 1916. And it became clear that it made some predictions that were just a little bit different from Newton's predictions about certain things, and in particular about the degree to which light would be bent in a gravitational field. So to test those predictions, all you would need to do is watch light passing very close to an incredibly huge object and see how much it was bent by, because these differences, it's a classic example of the incredibly small difference. Yeah. You only even have a prayer of observing it if the light is passing very close to something that has huge mass. The only thing that was close by, or relatively close by, that would do the job was the sun. So you had to watch light pass very close to the sun, but the sun is so bright that you can't see light in normal circumstances. The only opportunity for doing this test, for seeing if the bending was what Einstein predicted, was to observe light during a total solar eclipse, when the sun's light is blotted out, and to look at light coming from stars, which are just outside of the sun, you know, from the observer's perspective. So a great opportunity came up in 1919 because there was going to be a total solar eclipse. And what's more, there were going to be some stars in the background which were brighter than the stars that are usually, you know, randomly in the background during the eclipse. The only problem was you could only see the eclipse from a band across roughly the equator. So Eddington had two teams which had sailed off to, first of all, Principe Island off the west coast of Africa, and then to Brazil to observe the eclipse. So they went off, they made their observations. Then the results came back, and immediately things get very interesting, because there were in fact 3 different telescopes, because things go wrong. So Eddington had 3 telescopes, each of which made their own observations. Yeah. And the telescopes all gave different results. One of them gave results which were more or less in line with Einstein's predictions. One of them gave results which actually showed an amount of bending which was even greater than Einstein predicted and much greater than Newton predicted. So it kind of looks like it would falsify both theories. And one of them gave results which were much more in accordance with Newton's predictions.
And give me a sense, hold on, for Newton. So you have the sun now being blotted out for a moment by the moon, and you have these stars here on the side, and this light is what you're measuring, how that light travels to us. What would Newton's physics have predicted happens to this light traveling from these stars, which are, I guess, behind the sun, so to speak, or next to it or something, and that light comes to us?
That's right. So both theories predict some bending, or at least the way Eddington interpreted Newton, light would be bent. Yeah. And essentially the result of the bending is that if you just look up at the stars or take a photograph of the stars, they'll appear to be in a slightly different place from the place that they actually are. In fact, they'll appear to have moved outwards a little bit. So as the light comes past, it gets bent a little bit inward. You see that light, and when you see it, you extrapolate a straight line outwards and think that the star will be there, if you can kind of imagine in your mind. So what it will look like the star is further from the sun than it actually is. So what was happening with these photos was they would take a photo of the star field without the sun. So you'd have all the stars arrayed in their positions with no bending. And then the photos from the eclipse would show the same stars, and they would match them up and see if there was a shift in the positions. Now these shifts were microscopic on the photographic plates. Yeah. They were you know, well less than a millimeter. So it was, at this point, when the experiment is being done, after all of this traveling and equipment, you know, expense and precise equipment has been invested in this project, in the end, Eddington was looking at these photographs and using a ruler and a pencil and drawing lines to see if whether there'd been this tiny little shift of about, I think about 1/4 of a millimeter in the positions of the stars. And it was that shift that would tell us whether gravity was a force, like Newton said, or whether it was the effect of the bending of space-time, like Einstein.
Eddington is on team Einstein. He wants Einstein to be right. So he goes there, he actually goes out to say, I'm going to prove, which is not what Papa would do, that this theory works. And then he has 3 sets of data now, roughly, right? He has the photographs that say Newton is kind of right, Einstein is kind of right, and the other one we don't believe. There's nothing conclusive. On his millimeter scale with the little ruler.
That's right. So what he did, he did indeed want to show that Einstein was right. And so he engaged in a lot of complicated reasoning to argue that, in particular, the results that seemed to show that Newton was right had been had been created by a problem in the setup. So something had gone wrong with that telescope. He wasn't sure what had gone wrong, but he thought something had gone wrong, and that's why he got the Newton results. But the other results, which were quite incompatible with Newton and certainly close to Einstein's predictions, were too reliable.
Right.
So what we see going on there is not really the Popperian critical attitude, where you're supposed to take all discrepancies, be fair, take all discrepancies from what's predicted more or less at face value, but also not really the Kuhnian attitude, where you have a certain idea about the way things are going to be, and you're just kind of puzzled if they don't turn out that way. Eddington had the clear-sightedness of a Popperian scientist. He could see these results are a problem for Newton, these results are a problem for Einstein. Mm-hmm. But he had the kind of commitment of a Kuhnian scientist. He wanted Einstein to come out right, and he was prepared to do what it took to make it look like Einstein was right. So Eddington himself was surely correct in dismissing the Newtonian results. We can now say, looking back, that something must have gone wrong. But at the time, that was far from clear, and many of the other astronomers who read Eddington's papers thought that the argument was even a little bit fishy. So at least that Eddington was being too dismissive of one set of results and too quick to believe that the other set of results had no problems and should guide our belief. And this is very typical of the real scientific process, I think. This state that's somewhat in between Popper and Kuhn, where you have scientists being very partial on the one hand. They have their ideas and they want their ideas to succeed. But on the other hand, being very clear-sighted in a non-Kuhnian way and seeing which results need to be argued away and which ones need to be taken seriously. So science turns out to be much more Machiavellian, much more of a kind of a competition than either Popper or Kuhn really envisage.
And what you propose is they're kind of not the Kuhn Popper, but the Strevens rule. So you say this iron rule of explanation. You say what Eddington does here, he's looking at this set of data and he picks one that favors his theory. That's not quite what you mean. But can you say something about what you just said? Why does it become Machiavellian, maybe, also incredibly powerful?
That's a great question. It's Machiavellian because it's always possible in the way we've been discussing to say, well, something must have gone wrong with that equipment, or you people didn't do the experiment right, or you made some assumptions which look to me rather dubious, even though you think they're perfectly fine. Mm-hmm. So there's always scope for contesting the significance of any particular set of evidence. On the one hand, this is something about just simply about the logic of scientific argument, the way that evidence is brought to bear on theory. There's always scope for doing this. It's Machiavellian also because of the way that humans are. They want to win. They want to come out on top. They want their ideas to be right. And so they'll take advantage of this scope rather than being dispassionate in the way that Popper thought they should be dispassionate. And they'll seize on the shortfalls in another person's theory, and while doing their best to protect their own theory. So that what we see, and this has become very clear in some of the wonderful work that historians and sociologists of science have done on science in the wake of Kuhn. Kuhn persuaded them to look very closely at the way scientists really behaved, but what they discovered wasn't quite what Kuhn would lead you to believe. There's much more explicit contest. And there's much more in the way of attempts to actually change the rules. So for Kuhn, the scientists don't question the rules. Right. For Popper, I suppose they follow the rules. But what you really see often is attempts to change the rules, to move the goalposts, if you like, yeah. so that some kinds of evidence turn out to be the gold standard, not coincidentally the kinds of evidence that favor your own hypothesis, and some not.
But you're saying that this iron rule, which is the reason why we have science being this, if you say in a sentence here, it channels hope, anger, envy, ambition, resentment, to one end, the production of empirical evidence. So he's saying all these human dimensions of all these scientists who are competing and trying to satisfy their ego or whatever, be loved, recognized, and known, and be famous, they're channeling this messy human stuff into one direction. And you're saying they're doing this kind of to a fault.
Yes. So there is. So now I've talked a lot about changing the rules, about contesting the rules. I've talked a lot about disagreement. But underneath that disagreement, there is a kind of a constant set of rules to the game, which is that all arguments are conducted with evidence. Now, different scientists interpret that evidence differently and often partially, to favor themselves, or even when they're not being particularly self-promoting, they just have different ideas about what's plausible and what's not. So there's a lot of disagreement, but there's this fundamental agreement that when we do disagree, the way to go on is to do more experiments, to make more observations. And science is undergirded by this rule. And now that might sound very obvious when I state it like that, and it's certainly true of science, but think back again to philosophy, to Aristotle, or the medieval European or Islamic philosophers arguing with one another. They certainly take observation seriously, but they don't in any way follow a rule that says you must always argue using evidence. It's entirely possible to argue philosophically, to argue theologically. In fact, these are very important forms of argument. And when things go wrong, the thing to do is often not to do more experiments, but instead to do more philosophy, to decide who has the more philosophically coherent system. It turns out that's not such a good way. That's not such a good use of human resources. It's much better to go back and never mind the philosophy, simply do more experiments. And the discovery of modern science is really the creation of the system that makes scientists rather narrow-minded in a way, not the Kuhnian way, where they are narrow-minded because they think that one theory must be correct, but a way that transcends particular theories, but is still narrow in the sense that it says, always look for more evidence to settle your disputes. Mm-hmm. And that means that scientists are always creating more evidence. They're always making more finer measurements with more exacting equipment, or describing complicated structures like genetic structures, for example, in greater detail. And this is where we started, of course. It's precisely these details that ultimately do show you what's right and what's wrong.
And let me ask you about one thing, sorry, what's left out in this? So this kind of emphasis on producing empirical evidence and more evidence, and they kind of say, we're going to focus on this. The figure that becomes really important in your book is Isaac Newton, who you have in this kind of beautiful illustration. He just was able to compartmentalize. He knows mathematics and philosophy and religion and theology and poetry, and he knows all these things. But unlike Descartes, who kind of has it still together, Newton says, okay, I know all this, but I'm going to focus on empirical evidence as informing my science. And I'm interested in these two other things. So you said philosophical argument, causality or things like that, or aesthetic beauty could be two other reasons that would give you the incentive to believe in one theory over another.
Yeah, Newton was a wacko, but a wacko in a way that changed the whole world for the better. Right. So for some reason, even though he wrote a lot about philosophy, almost all of this was unpublished, by the way. So it took a long time to discover that he had the many interests that he had, but he was quite happy to dive into philosophical argument, just the same way Aristotle would have, or Descartes. But for some reason, and I don't know that we'll ever know what this reason is. For some reason, when he was doing physics, so when he was constructing his theory of gravity, he left philosophy completely out of the picture and simply asked himself the question, what theory will best explain the exact observations that we make, the exact trajectories of the planets, the exact trajectories of falling objects, of cannonballs fired into the air, and so on. So we know on the one hand, he had these philosophical interests. He was not only able to, but actually quite interested in arguing with someone like Descartes about the philosophical principles underlying physics. Descartes and Newton didn't quite overlap, so Newton could never have actually argued with Descartes. Descartes died too young, but arguing with him on paper, we have these things Newton wrote. And yet, when he turned to do the physics, it was as though that stuff didn't exist. This is the compartmentalization. He started doing it in the way that a modern scientist would do it, attending to empirical evidence only. But he wasn't doing it because there was some rule there, what I call the iron rule, the rule that governs all of science. That really didn't exist yet. There was just something about him that made him operate with this very narrow constraint. And it was so successful that after him, in the 100 years after him, everyone saw he'd been so successful doing physics in this way, they said, we should do it too.
And you track this kind of single-mindedness to say, I'm capable, I understand. I guess one philosophical reason would be, you don't just look for the law of gravity, but why is there such a law? That it corresponds to some greater meaning, God is behind it, or there's some other law, right? And he said, I'm interested in this, but I'm not doing that when I'm doing my science. And then you track this to today or contemporary science, and you have these, I really love when you were sort of engaging with Neil deGrasse Tyson or Stephen Hawking and Lawrence Krauss and people like that. How do they deal with this other idea that there's beauty as an argument for theory or its elegance, or that there's a philosophical deeper reason? It surprised me to say when you said that a third of the scientists working in the United States believe in the existence of God. Because what you're also saying, you have to put that aside when you're going into the lab or into the observatory or into the field.
That's right. So a little more subtly, you put these things aside when you publish. So it may very well be that even religious considerations influence the kinds of experiments you do, the kinds of ideas you have, and nobody's going to stop you from thinking those thoughts. But when you publish a paper, it's got to be just the facts, just the experimental facts. And the case of beauty, which you just mentioned, is a wonderful illustration of this. So if you read the popular writings of modern physicists, or even just go to their talks, see what they have to say, you'll sooner rather than later, you'll hear them praise beauty or elegance as a sign of truth. So again and again, you'll hear someone like Murray Gell-Mann, who was one of the developers of quark theory, this idea that all of the different apparently fundamental particles that have been observed can, well, not all of them, but the great majority of them can be understood as just different combinations of the same very small set of even more fundamental particles, the quarks. So wonderful kind of beautiful story about how we get a great diversity from just a few elements. Gell-Mann said, yeah, one of the things that really guided me to this theory was thinking about having a simple, elegant, beautiful, symmetric organization of the particles. Mm-hmm. And when I came across this particular way of organizing them, I could see from its elegance and its beauty that it was the one. Now then he turns around, and having come up with this idea, which won him a Nobel Prize, he, of course, publishes it in the physics journals. Here is where the iron rule comes in. So although Gell-Mann himself and many of his contemporaries believe that the elegance of the theory is a strong reason to believe that it's correct, you simply can't say that. He can't write a paper saying, I've come across the most wonderful system for organizing the particles. Instead, you lay out the system, you go back to this paper, and you can see this happening. And then the question is, okay, now what experimental evidence can we dig up for the system? And the answer is, one of the answers when he first started to publish his system was, it predicts the existence of a new particle. We have one of these structures, and that structure has space for 10 particles. And we have 9 particles that fit 9 of those places in this beautiful structure whose symmetry is characterized by very esoteric mathematics. And then there's this missing an empty space. Gell-Mann says there must be a particle to fill that space, to fill out the structure. And this is something that can count as a scientific argument. The beauty of the structure, it doesn't count.
Okay.
But if that particle is observed, that's empirical evidence for the structure, and that counts. So what we have to do is not, Gell-Mann has spent time and effort with his pen and his paper sketching out these theories. But what we now need to do is get hundreds of people, spend millions of dollars, and months and years of work just firing particles through a particle accelerator and pondering, poring over the thousands, tens of thousands of pictures we get of different interactions from those particles, looking for a certain little pattern in those pictures that will tell us that this particle, the omega minus particle, actually exists. So the need for evidence above and beyond beauty is what motivates people to devote these enormous resources to making the observations that ultimately are what makes science so powerful.
What do you make of you give these examples of people devoting 5 decades of their lives trying to get evidence, really being determined and dogged, and they're kind of the Kuhnian scientists who are working, so just observing finches or whatever they're doing. And then there's also physics today that doesn't have any evidence, and we may never find it, or because you said we would need to have, like, on the scale of the universe, some experimental possibilities. So what about science that doesn't get this evidence? And is it still, in a naive, non-scientist way, is it still correct?
That is very much a very controversial question right now. So there are the aspects of string theory, attempt to give an even more fundamental story about where particles come from than Gell-Mann's quark theory, where it seems that although it's possible in principle to build an experimental setup that would test the theory, that setup would be, now these are all kind of guesses, but the guesses are absurd. We would need particle accelerators the size of a galaxy.
Right.
But we're not going to be building those anytime soon. In the meantime, what do? Some proponents of string theory have said we should change the rules of science. We should change the fundamental rule, the iron rule of science, to allow arguments for beauty to actually count.
Okay.
So it would be possible to say for the first time, well, I have no evidence for my theory, but it's so beautiful that I think we should consider it true, or at least take it very seriously. And many scientists have unsurprisingly pushed back and said, that's not science. That's not the way that science works. In science, you must have empirical evidence. And if you don't, if it's just too expensive, if it's impossible to generate, then that's, I'm sorry, but we just have to console ourselves that we're never going to find out the truth about these things. At least we're not going to find out the truth in the scientific way.
My question would be kind of a question that Nietzsche would ask. Why privilege symmetry over asymmetry? Why privilege harmony or simplicity over messiness and complexity? In some ways, I get what you're saying, that beauty, that these scientists are saying we may change the rules. But that beauty itself, why would that be the standard? Why not ugliness or messiness, or there's other categories? It's kind of an interesting idea that we would privilege this one thing because God gave it to us, probably not, because we as, and this is interesting whether you think that, because we as human beings are drawn to these things, because we do know what beauty is. We have an experience of it.
It's almost in the very nature of beauty that we're drawn to it, right?
Yeah, right.
So these are good philosophical concerns and arguments about the real power of beauty. And this is where we would be headed if we did suspend the iron rule. The next question would be not just should we accept a theory because it's beautiful, but whether beauty is really, after all, a sign of truth. Now, many physicists would say, oh, but we've done so well pursuing beauty.
Yeah.
Newton's theory was beautiful. The quark theory was beautiful. Einstein's theory was beautiful, as Eddington, the eclipse observer,
Yeah.
remarked many times. So far, beauty has been good for us.
And let me go back to the Einstein example for something else. So when I learned this example, and I took this class, History of Science, in college, and I'm not a scientist, and it's not my forte. So I offloaded this to my son, who's studying astrophysics, and he does things that he's a junior in college, and I have no idea what he's observing, and he's studying images all day, tiny little images. So I heard this anecdote that Einstein is asleep. He's taking a nap, and someone wakes him up, the housekeeper or someone, and says, Dr. Einstein, we got some news. A cable came in from Eddington, presumably from the south, as if he processed the data right there. It proves your theory. And he says, why did you wake me up from my nap? I knew it was right. That he did not need evidence. That I always love this anecdote. I'm sure it's completely apocryphal, but I love this anecdote that Einstein said, why are you waking me up from my 30-minute nap to discover this? I knew it was right.
That's right. I mean, in a way, what Einstein said is what Eddington what Eddington acted out.
Yeah.
He was convinced enough about the theory that he did not ignore the evidence. Of course, he took great pains to generate the evidence, but then he was going to take the part of the evidence that conformed to the theory much more seriously. And so I think Eddington was certainly driven by the beauty of the theory, as Einstein obviously was.
Yeah, yeah.
However, as I think were Kuhn here, he would say, this is the way science, if scientists were simply happy to rest on the beauty of a theory, then we would probably still be with Newton, or maybe we would still be with Aristotle, who knows? Those were beautiful theories too.
Okay.
It was only because we were forced by the need to dig up the little facts that we discovered that something wasn't right. And at first we could dismiss those facts and say maybe there was something wrong with the equipment. Mm-hmm. That's what Einstein would have said. That's what Eddington did say. But if you go back again and again, and every time you get the discrepancy, then you start to think, well, maybe this theory is beautiful, but wrong.
And your description of science, as you're calling it, there's an irrational dimension of the irrationality that created modern science. What do scientists think when you talk about it in this way? Because a lot of people, I think, would not want to be characterized as doing something irrational.
Right. The irrationality comes in the narrow-mindedness that only looks at evidence and not at other things. So someone like Gell-Mann, when he publishes, although he believes, like many physicists, that beauty is an important guide to truth, nevertheless, he's prohibited from actually mentioning that fact.
Yeah.
And not being able to take that into account is what I call irrational. And not bringing everything that's relevant to assessing the theory to the table is irrational. It's an irrationality of omission, if you like. So it's certainly true that scientists think of themselves as being very rational. And the reason for that is that in so many different respects, they are very rational. Mm-hmm. I mean, perhaps not in their private lives, perhaps not when they're, engaging in some of these behaviors like special pleading for their theories, but in many ways, they're extremely careful and they're rule followers.
Yeah.
So, but they're put in a difficult position by the iron rule, which tells them that as part of following the rule, you must ignore this consideration that you take to be, in fact, very important.
As a philosopher, do you think this is, how does that actually play out? I understand that you go to work and you kind of check your, religion at the door or something like that. But as a philosopher, do you think there is it doesn't sound like it from the book, there's an issue that it sort of diminishes the human potential of scientists. You're saying it's just a way to do work, right?
I think that's right, although there's a bit of a catch. So for a scientist can follow the rule and they can say, oh, I see why I'm doing this. And even though it's in a certain sense an irrational narrowness, it's a narrowness that will ultimately will ultimately be good for science.
Right.
And so when I explain my ideas in this way to scientists, they typically okay with that. They'll say, yes, okay, well, in that case, I can see on the one hand why you say it's irrational, but I see you're not undermining science. You're explaining, and quite the reverse, explaining why it works so well.
Right.
However, I do think that to some extent, the whole system of science education takes shortcuts rather than explaining carefully to science how science really works and why we do things this way. There tends to be a kind of an imparting of a kind of empirical mindset that encourages scientists to dismiss considerations other than experimental evidence out of hand.
Mm-hmm.
And that's where some of the figures I quote in the book you mentioned earlier, like Neil deGrasse Tyson or Larry Krauss, who can be especially contemptuous of philosophy. I think what they're doing there is something that I'll say, first of all, is good in a certain sense, because they're encouraging scientists to ignore philosophical arguments. And as I've said, I think that's a good thing for scientists to do. But they do it in a way that rather than giving scientists a sophisticated understanding of why they should focus entirely on the evidence, rather gives them more of a kind of a blunt prejudice in favor of the evidence. A prejudice that, is to some extent incompatible with this beauty worship.
Yeah, it's interesting. I was quite interested. I really like those chapters where you say sort of building the scientific mind or science and humanism, where you talk about how actually this iron rule is implemented. It's actually taught, and you have to be taught how to actually accept that this is producing evidence is the only standard. And you say something here about how science is a bit of a machine that reproduces itself by bringing people into adherence with its policies, its procedures, not in the Kuhnian sense anymore here, but you're saying by making this iron rule the paramount rule. And I guess the difference, if that's right, and correct me if I'm wrong, Kuhn would say, no, people don't just leave these things out. They sort of say, I know that there's beauty and God or meaning or something. I'm just going to do my science. They actually cannot hold that other world view. In some ways, he's saying you cannot. And I wonder whether Kuhn, who was both incredibly proud, I think, that his book had this impact, and incredibly chagrined that it was misunderstood so much, I think, kind of furious. But would he say a scientist can have a belief in God or religion and also do science? Or would he say these are incommensurate worldviews?
I think he would say something he wouldn't be yes or no on that. It would depend. So a certain kind of science might actually build in God. God would be part of the paradigm.
Okay.
And part of what you're doing when you do the science is to fit things into the divine plan.
Yeah.
I would take an example which maybe is a little bit closer to our modern sensibility, that beauty is a part of the paradigm. So the particle physicists' concern with beauty and elegance and symmetry is actually part of the paradigm of modern particle physics and guides their research.
Yeah.
And in a way, he would be right, that because that is a very, perhaps not universal, but a predominant mindset. But I think he fails to notice the fact that in the official products of the paradigm and the published arguments, beauty is entirely left out.
Right. But that's really, that's actually nice how you just corrected me in a way. So like you could have God or beauty inside your scientific paradigm. It's just another paradigm. There's probably science like that. So can you say something about, as you know, I really love Kuhn. It was sort of, for me, I had an assignment in college, which was, we had to study for this class and study everything. And then we got the take home final, and it said, write 10 double-spaced pages summarizing Thomas Kuhn's book. That was the entire final exam. And to this day, I think it was the best assignment I had in all my education, because it made me read that book. And I remember where I was, what I was doing when I read this book in college. This idea of paradigms became so powerful. So part of what we're organizing the series here. So I interviewed Richard Schechner, who rethought what performance is, when performance used to be up on a stage in a box and you're sitting here, and he says, no, the moment you arrive at the door of the theater, you're already in a performance. Performance is a much broader practice, cultural habit than what we think performance is. So he shifted in the 60s the entire idea of performance. Or Carol Gilligan, who asked, how is human development constructed, and leaves out the fact that actually some experiences are considered universal when they're not. And she started listening to women to challenge what humanity is. But why does paradigm become so powerful? And how is it, as a philosopher, what do you think of when people use it the way I use it, in this kind of casual or kind of popular way?
Well, I don't object to that. What's happened is it's become a very flexible tool. Yeah. So sometimes when people talk about paradigm shifts, they're talking about something that's still somewhat on the Kuhnian scale, where there really is just everything shifts, and suddenly you see the world in a wholly new way. Perhaps, for example, some new artistic movements function. There's a sort of a change in the way that you see things on that scale. It's not science, but there's still a change in worldview. Yeah. But often people use it in a rather narrow way. Interestingly, Kuhn himself found himself, perhaps not by choice, forced to use it in a narrower way. As people who are thinking about science, historians, sociologists, and philosophers, look more closely at science, they saw that the thing that was performing the role of the paradigm, the Kuhnian paradigm, the kind of the recipe for doing science, was often not some great world-spanning idea, but something very specific and actually rather confined. It would be using this particular kind of technology, like a certain genetic sequencing technology, for example, or a certain kind of microscope, and everything would be built around using that tool. And the paradigm was really a much smaller thing. Yeah. So Kuhn started using it in that way himself, and certainly people who were his fellow travelers did. And in the same way, in broader society, we sometimes, or even perhaps often, use paradigm for something that's not a change that goes down to the very foundations of the way we think about the world at all. It's just a new way we're teaching our classes.
Right, an explanatory framework, right.
Like we're flipping our classes, and we watch our lectures on video, and then in the classroom we do discussion instead. That's a great new idea, and it really changes things. Right. And it's a paradigm shift, but it's not
a Kuhnian paradigm shift, right? It
hasn't changed, right?
Let me ask you two really big questions at the end, because it's kind of vaguely. So chapter 10, I think, in Kuhn, as far as I remember, is this question, or he did this in the postscript too: is there progress built into this, or could we imagine that, in a more Kuhnian sense, roughly, there could be a paradigm and we could regress, and there could be a less powerful or productive theory that could substitute or replace an earlier one, that there's no inherent, because we like this teleology that everything gets better. Quark theory replaces physics. Einstein is better than Newton. That's my first question. And then the second one, which you've gotten a lot, is where we are right now with climate change as an example. Your idea of the irrational dimension, do you think science has a way right now to help us out here in what most people think is another type of crisis? So the first one is there progress in science?
Well, Kuhn always said that when there's a paradigm shift, there's always a loss as well as a gain. Mm. And we hope that usually it's one step back, but 2 steps forward, right? Yeah. And I think Kuhn thought that on the whole it was, although he was reluctant to say exactly what progress consisted in. And I certainly think that it on the whole it is. Yeah. So yes, although it's never as simple as something being wholly better in every way. Mm-hmm. If we look back in the long term, and Kuhn certainly thought this was true, we can see a definite arrow of progress pointing upwards, which is to say, there may be little dips and so on, but the long-term trend is upwards.
Oh, so let me connect this directly to this next question of climate change.
Yes.
I know, and you know, there's activists and people who are saying, we've gotten ourselves into this mess. by our incredible emphasis on science and technology, and we've kind of engineered ourselves into this crisis because we're consuming too much, etc. And some people are skeptical that science is going to engineer our way out of it because we're in it because we're over-consuming and overproducing.
Well, I think science is a tool, and tools can be used to do good things and bad things. But there's no real question in my mind that science has a lot to offer in terms of ameliorating all the damage that it's been used to cause. Mm-hmm. So we already have a lot of engineering of renewable power resources. Solar power and wind power have become so much more efficient, mm-hmm. And so much less expensive. And a lot of it is, I suppose an engineer would say, engineering rather than new theoretical discoveries. Yeah. But still, that's science broadly speaking. And likewise with electrical cars and so on, we have another way to cut down on emissions. Science had better be a part of the answer, because I don't see the human society making all of the sacrifices that are necessary if there is no further technological innovation. It'll be a little bit like well, COVID. After the first wave of enthusiasm, people they're trying, but they're not trying as hard as they need to.
Oh, you mean in terms of sort of like the proper way of sort of behaving right now in the pandemic? Yeah, there's fatigue setting in, definitely. And I'm going to leave this whole question of the distrust of science. I think it's a sociological question and not a political question, not a science question in itself. You do hint in your book a little bit at that this kind of irrationality sometimes leaves people exposed to being surprised when non-scientists talk about science. You have a reference to the science wars in the 90s, and where scientists said, what they're talking about science? I don't even know what science is. And you're saying this irrationality can produce a kind of narrowness that leaves it exposed to other people just turning it into a caricature.
Right. So on the one hand, scientists are not really in such a great position to defend science. But on the other hand, or their defenses, I think this explains a lot of what has gone on with the distrust of science. Give non-scientists an unrealistic sense of how science really works. Yeah. They buy this picture of the scientist being impartial, always critical, always attentive to evidence, and there being a general kind of agreement on what the evidence shows. Well, none of that is really true of science. When people go to science and they discover that this picture of impartial, rational, objective sifting of the evidence is wrong, which it is, mm-hmm. They think, well, then it's simply a matter of anything goes. It's just like anything else in life. Whoever has the positions in the right institutions, the fancy universities, simply gets to push everyone else around. Mm-hmm, mm-hmm. And if they decide to push everyone around in a way that I don't like, then I'm going to push back.
Yeah, interesting. So your book is actually doing a service to explain a little bit more carefully what is the scientific method, to not arrive at these kind of foreshortened perspectives that this is what scientists, which then says, well, if that's what it is, then either it's ego and power, or it's actually this kind of disinterested, non-human kind of super rationality, which you say it's neither. There's a kind of decision where you keep on sort of staving off the other parts to arrive at some result and evidence.
That's right. So there's all of this disagreement and jockeying for position, and sometimes just straight out pursuit of self-interest. What that's doing, thanks to the iron rule, is that energy is, as you said earlier, that energy is being channeled into producing yet more evidence. So even as people are disagreeing with one another and throwing up in this general chaos and confusion about who's right and who's wrong, the pile of evidence grows, and it grows to the point that people start to see that what's working, what really is working, and what's really not working. And so the truth does emerge over time, or at least we improve maybe our theories will never be completely correct, but they become closer and truer to the way things really are.
Michael, I really want to thank you. So you did really me a fantastic service to do a kind of two-part conversation. You explained how science operates and sort of the Kuhn or Popper models, and then you yourself are shifting a bit of a paradigm of the understanding of science. So you have both the role of the meta explainer of how do paradigms work in our series, and the one whose book, so The Knowledge Machine right here, which among your other books, this one is out right now, 2020, so people should order it from the independent bookstores. It's incredibly readable, and I wrote this to you. It was really just incredibly fun to read for somebody, and I'm not saying this in a sort of silly way for a non-scientist, but to stay engaged. It's in these kind of really complicated discussions, but for you to stay in them and not just turn them into abstractions is really wonderful. So I want to thank you for that, and also you know, I was really afraid you're going to break my heart though, because I love Thomas Kuhn so much, and you didn't. So
well, that's wonderful to hear.
That's a true philosopher, yeah, because you sometimes think, you know, when your intellectual heroes get taken down, and Kuhn has a lot of people have done that, but I always feel there's still something worthwhile.
There's something in there that is the key to understanding
That's
exact how strange science is, and really why it has been able to do all of the wonderful things that it has done for us.
So that's great. So Michael Strevens from NYU Philosophy, thank you so much for being part of the series. And then we'll put all the links to your other works in the notes to this Skirball series.
Great. Thanks so much for inviting me.
Thank you. Okay, take care. Thanks so much.